Good morning, everyone. My name is Farhat Beg, and I'm from Center for Energy Research and Department of Mechanical and Aerospace Engineering here at UC San Diego. Today, I'm going to give you an overview of our Z-pinch research. Uh, I'm not going to talk about everything on Z-pinches we do here. The reason being is that Jeff Narkis, he gave a talk a couple of months ago, I believe, where he talked about the mitigation of Rayleigh-Taylor instabilities using external magnetic field and then using multiple liners and the combination of magnetic field and multiple liners. And we have been carrying out experiments on those ideas. And I'm also not going to talk about the work that Nick Abar has been doing, where he's using high resolution spectroscopic techniques to measure the magnetic field distribution in Z-pinch plasmas. And I believe he has a talk coming up in CMEC seminar series. He has done experiments on Weizmann Institute, which he published a couple of months ago in PhysRev-E, and he has done experiments here on our machine where he has determined magnetic fields. So he will be going in detail on that aspects. And the third thing that I won't be talking about here is the liner pinch work, solid liner implosion on the gas that we will be doing, and is part of Dana Zimmer's project. And the fourth thing is the astrophysical jets. So when you use two conical wire arrays, the supersonic plasma flow takes place from this conical wire arrays, and you generate bow shock, and there's energy deposition, and Pia will be doing experiments on LTD pulsar. We have done experiments on our small machine, which was published. The results were published in PRE last year. And there will be a talk on that topic to cover every aspect of that. So I just wanted to say that what I'm going to present here is a limited work that we are doing on Z-pinch. There's a lot more work that goes on. And the work that I will be presenting is supported by NNSA under our CMEC award. And the DPF work that I will be presenting will be supported by Air Force. What I would also like to mention here, I cannot see the chat, so if you have any question, stop me at any time. I want to make this informal. And Miriam, if you see any question in the chat, please read out, because I cannot see chat in the full screen. And I also don't want to be like that professor who gave a lecture for 2 hours and realized that he was muted for 2 hours and his students didn't tell he was muted. So if you don't hear me, this is the time to tell me that you cannot hear me. So before I go into Z-pinch work, I just like to mention that the grand challenge that we are addressing under CMEC is exploring change in material properties under extreme conditions. And when I'm talking about extreme conditions, I'm talking about extreme conditions of temperature, pressure, and magnetic field. And I don't want to ignore another aspect here, and that's the density. So we are also creating extreme conditions of density, meaning very high densities. So we have divided our research area, research into 3 thrust areas, and they are all interlinked. thrust area 1 addresses questions pertinent to energy transport in high energy density science systems. And when I'm talking about high energy density science systems, uh, we are using various tools to address these issues, whether it's energy transport in magnetized plasma using laser plasma interaction, driving shocks, or using pulse power devices to create these systems. And you can see here the partners who are collaborating in addressing these questions. Thrust area 2, which is material properties across AGD regime. And you have heard over this year several talks about this various HED regime. And the third thrust area is nature under extreme condition. That basically deals with astrophysical plasmas, meaning laboratory astrophysics and planetary science. And we are creating those conditions in the lab using high power lasers or pulse power ZPG. So when we are talking about these three thrust areas, they have synergistic physics, laser plasma interaction. We are dealing with equation of state, whether you're using pulse power ZPGs or laser plasmas. And we are dealing with radiation in all these thrust areas. And magnetic field and energetic particles also play important role. The tools are already described to you that we use high power lasers. And the cool thing and unique thing about what we do is that we go from large scale facilities from Z, NIF. These are state of the art facilities. We do experiments on both facilities. Then we go to facilities like Omega, where we carried out experiments. And then we also do experiments on facilities like Jupiter Laser Facility at Lawrence Livermore National Lab and Texas Petawatt Facility at University of Texas, Austin. And then we have some in-house facilities like linear transformer driver here at UCSD. Or gas gun at UC Davis. And we use a variety of diagnostics, targets, and codes, PIC codes, radiation hydrodynamics code, Monte Carlo codes, so you name it. And of course, what we are doing, a number of applications, as I mentioned, in astrophysical plasmas, planetary physics, and also in inertial confinement fusion. So my focus today is on Z-pinches. So those of you who are not familiar with Z-pinches, what is Z-pinch? It is the simplest magnetic confinement device. You see a cartoon on the right-hand side. What you have is the electrode with which you have a capacitor connected. I'm just using very simple configuration here. And in this chamber, you fill it with a gas. It could be deuterium, hydrogen, argon, neon, whatever. And then you apply the voltage across these electrodes, and the breakdown of the gas takes place. Current starts to flow in Z direction. That's why it's called Z pinch. So, or in axial direction, and there is a self-generated magnetic field. And then you have J cross P force, which compresses this gas to the center. Doing work on this gas, heating the gas, PDV work. And as you're compressing, you are the density is increasing and the temperature is increasing. So what we want to know is the when we are talking about traditional and conventional Z pinch, we want to know what is the pinch radius when it is compressed to the axis, what is the peak density, and what is the current distribution. The reason I have put this in blue, current distribution is extremely challenging to determine in Z pinches. And that is very important parameter to know uh, for the validation of the codes. And particularly in Z pinches, if instabilities are formed, then we want to know where the current is flowing. And these three parameters plus temperature, why these are important? Because these parameters can influence the potential applications, uh, particularly in magneto-inertial confinement fusion. And they can also determine the stability of the devices. Stability of Z pinches is extremely important if we want to use it for applications in fusion, for example. There are certain parameters that we can control. For example, we can control what amount of current flows in the plasma, and we can control the line density of the pinch. Before I go into the details, just to those of you who are not familiar with Z pinches, I just like to show what kind of conditions you can create. And this is a slide taken from colleague from San Diego National Lab, Mike Cuneo. So what you see is B equal to mu naught I over 2 pi r, right? So magnetic pressure is equal to B square over 2 mu naught. So you can see that the magnetic pressure is proportional to the square of the current. So 1 megajoule of energy corresponds to, if you take that F-150 truck and it moves with 60 miles per hour, then the kinetic energy is about 1 megajoule, which is 0.48 times the energy in a stick of dynamite, or 100-watt light bulb uses 1 megajoule in 2.8 hours. So and the velocities that we create with Z pinches could be of the order of 500 kilometers per second. So you can travel from New York to LA in 8 seconds. So here is another example. This is the mass of the F-150 truck, about 3,000 kilograms, and this is the velocity. So what you have is the energy of 1 megajoule, and you can see if you have that kind of collision, what kind of energy is released. So when we are talking about in Z pinches, in 1 megajoule, energy is released in 5 nanosecond, and that's we are talking wide array Z pinches. Let's talk about historical perspective. First, initial experiments on Z pinches were in 1790 in defense industry. That's interesting. In 1790 defense industry, these experiments were done in Holland. What you see on the left-hand side is the picture. This 100-liter jar discharged into 1 meter long wire, and the energy store was about 1 kilojoule. So when you discharge this jars into the wire, you are going to create the plasma. So this was the this is one of the first example of Z pinches. What you see on the right-hand side is the patent by Thomson and Blackman at Imperial College, where they showed that you can use linear gas discharge devices to create fusion. So Z pinches have variety of configurations. I'm not going to talk about those, all of those. You see some examples here. On the top, you see the wire array Z pinches or fiber Z pinches. This is the Schlieren images taken from experiments done on MACPI generator at Imperial College. On the right-hand side, you see dense plasma focus where the current sheet is collapsing on the top of the anode, and you see instabilities form. And here you see the wire array Z pinches that were very popular and still are popular in 1990s for X-ray sources and for uh, inertial confinement fusion. And then you have X pinches and gas puffs. So my focus today will be on gas puff Z pinches, dense plasma focus, and X pinches. There are other configuration, for example, frozen deuterium fiber Z pinches. They were at one time were investigated as fusion energy source using concept of radiative collapse. Then there are sheared axial flow pinch. My colleague at University of Washington is working on this concept where they are using sheared axial flow to stabilize the pinch. It's called ZAP pinch. And they have generated significant amount of money to pursue this concept um, privately. And then there's a liner-driven pinches, wire array pinches. One pinch that I would like to point out here, though I'm not going to talk about, is laser-driven pinch. What is laser-driven pinch? So when we were doing experiments at the Vulcan laser, what we realized that when we shoot the laser, we started to see the instabilities form in the stack, which was holding the target. And we started talking to Jin McCall. If you are, if you've been in the field for 30 or 40 years or more than, you may know Jin McCall. He retired 20 or 30 years ago from Los Alamos National Lab, where he carried out experiments with carbon dioxide laser. And when you have a laser hitting the target, you are creating fast electrons, and these fast electrons leave the target. So there is a charge imbalance. And due to the charge imbalance, there is a return current that flows into the target. If you are using the wire to hold the target, then it becomes a Z pinch, and it is actually very fast Z pinch because the current return current is only rise time is limited by the inductance of the target. So you can have 10 nanosecond current rise time. So it's a very good for studying the growth of instabilities. And since then, Mario Manuel, when he was student at MIT, he did experiments on omega and he saw the similar effect, and he wrote applied physics later. And recently, last year or two, Jorge Roca at Colorado State University, he did see the same thing in his experiments, and he wrote a paper for PRL. So there's some history on laser-driven pinches that started in 80s by Jane McCall and tested on long pulse lasers to short pulse lasers. So Z pinches have a long history, the neutron and X-ray sources and also fusion sources. And this is the chart made by my colleague Christini when he was at San Diego National Lab, and we have modified this. So let's start with 1950s, where linear deuterium Z pinches were used for fusion. And at that time, in late 1950s, dense plasma focus was invented both here in the US by Mathur and in former Soviet Union by Filipov. The operating mechanism is the same. It's just the aspect ratio of the electrode is different. Again, I'm not going to go into the details, but what I would like to point out, when this device came out and the neutrons were detected, and it was said, wow, okay, dense plasma focus is going to be used for fusion. And actually, there were a couple of papers written about dense plasma focus for fusion reactor as well. But later on, more detailed work showed that the neutrons that are coming out uh, are not due to thermonuclear fusion. They're also due to beam target mechanism. So linear deuterium, and there's still interest in dense plasma focus from various points of views. For example, you can use this as intense particle source, whether it's ions or electrons. You can use ions for material damage studies. Flippy reminded me yesterday, he's a postdoc at UC Berkeley, that he worked on this device to do a material damage study. You can use that as a neutron source or ion source. Colleague Andrea Schmidt at Lawrence Livermore National Lab, she's been doing experiments using 1 megajoule DPF for neutrons and ion production. So let's talk about linear deuterium Z pinches. It has evolved over the years. As I said, fiber Z pinches were very popular due to radiative collapse effects to produce thermonuclear neutrons. And also it was suggested that if you go above current of 1 megaamp, Peace-Brzezinski current, then you can have satisfy Lawson criteria, and that was the basis of building MACPI generator at Imperial College. And then there was wide array experiments done at San Diego National Laboratory, where dynamic hologram concept was proposed for fusion. And then these Z pinches are also used for K-shell radiation sources for from 1 to 10 keV range for radiation effects physics. And there was work done for X-ray laser. Jorge Roca, for example, started work on capillary discharges to produce lasing on those discharges. And now let's talk about pulse power Z pinches, where at San Diego National Lab, experiments were done. Initially, experiments were done, I believe, in Physics International with a small number of wires, like 4 wires, to produce X-ray sources. And then at San Diego National Lab, when the number of wires were increased to 300 or more, then the significant X-rays were produced of the order of more than megajoule. And here you see 250 terawatt of X-rays produced with 18 megaamp generator, and that was the use for X-ray applications and also for driving the hologram that I mentioned. And recently, there is a work going on maglev concept. I'm not going to talk about maglev concept. There, ARPA-E started a program 4 or 5 years ago where they invested in new fusion scheme, magneto-inertial fusion schemes to investigate parameters that are in between what is happening on ITER and also on NIF. And that work is still going on. Some of that work has now is being supported by industry. So this is the whole history of Z pinches. So when we are talking about traditional Z pinches, it's in force balance, and you can see equation of state, equation of motion. You have the pressure gradient in the plasma, and then you have J cross P force, which is compressing the plasma. And if you simplify this equation and use this assumption that quantities only vary in R, and your Z pinch is long, so there are no end effects, meaning there are no heat loss to the electrodes. And if you use Ampere's law, then you get this relationship called Bennett relationship. And you can see the Bennett relationship is the, it relates temperature with the current. Again, no instabilities, nothing. We are assuming uniform plasma. So you can see if you have higher current, you can have a significantly high temperature. For example, if you have 1 megaamp current generator and the line density of your hydrogen plasma or deuterium plasma is 4 times 10 to the 18 per meter, then you can generate 10 keV temperature. This is the temperature you need for thermonuclear fusion. So that's exciting for limitless energy, but it's not as simple. Are there any questions? Any questions in chat, Miriam?
No questions.
Okay. So my postdoc advisor, Professor Malcolm Haynes, he showed that Z pinches can satisfy Lawson criteria. And he showed that the Lawson criteria is the product of density and confinement time is 510 to the 20 second per meter cube. So you are ohmically heating the plasma when you are passing the current. So the assumption he used in this paper is that the confinement time is determined by losses to the electrodes. I mentioned that, and the pinch is in radial equilibrium. And he showed that the 100 nanosecond time scale leads to the density of 510 to the 27 per meter cube, and the radius about 20 micron. And if you have a pinch length of about 9 centimeter, then with 1 megaamp current, you can achieve this kind of conditions for thermonuclear fusion. And as I pointed out, this was the basis for building MACPHY generator. But there was a big condition there that the pinch is stable for 1,000 growth MHD growth times. This is the MHD growth time, which is equal, which depends on the Elfman velocity over radius. And that was the big assumption. And when we carried out experiments for my thesis work at Imperial College, and we observed that pinch becomes unstable within 10 nanosecond of the current rise time. So the instability growth time is 5 to 10 nanoseconds. So it's initially very unstable. So that's why at that time, folks moved from fiber Z pinches to wire array Z pinches. Let me see how I'm doing on time. Okay, so now let me move on to gas puff Z pinch experiments that we are doing here. What you see on the right-hand side is the plot, I believe is taken from John Giuliani's review paper, and I would encourage postdocs and students to read this paper. It is very comprehensive. What you see here is the peak current versus neutron yield, and you see there are two pulses. There are two lines, one for the longer pulses and one for the shorter pulses. And what you see here is the variety of single shell, double shell, long pulses, failed gas puffs. And you can see that when we are talking about 10, 20 megaamp current, you can achieve 10 to the 13 neutron yield per centimeter. So when we are talking about gas puffs, you can use a variety of configurations. You can use single shell, you can use multi-shell, you can mix gases, and that could also affect your pinches. Jeff Narkis, I believe, in his presentation, touch on that. And when we are talking about mid-scale or small-scale experiment, gas puff load is very attractive because you can take tens of shots in a single day or hundreds of shots in a week. And you can use a wide range of gas densities and species. And what you see here is the schematic of gas puff. So this is the double gas puff nozzle we use for some of our experiments, and then you inject the gas between anode and cathode, and you apply the voltage. Current flows through the gas. The plasma current flows through the plasma, and you have self-generated magnetic field which compresses. So I already explained this to you. So we have carried out experiments on a linear transformer driver. This is the latest technology developed initially collaboration between Sandia National Lab and Tomsk in Russia. Now Sandia is leading development of this technology. It is a simple technology. It uses low inductance switches, so it doesn't have many stages as you would have in Marx bank technology, where you have capacitor bank, Marx bank, where you charge the capacitor in series and in parallel and discharge in series. So you have a pretty large energy storage here is 130 kilojoules and 1 megaamp current, and the current rise time is 100 nanosecond. The LTD I'm talking about has 12 kilojoule energy, is about 1 megaamp, and the rise time is 150 nanosecond. And it doesn't have as many stages at Marx and pulse forming line based machines. So when we started to do experiment, first question was how efficient energy coupling is in linear transformer driver compared to Marx bank system. And that's what I show you here, the simulation done by Jeff Narkis using Mac2 code. Later on he did simulations using Hydra code as well. So what you see is that on the top LTD pulsar, where you see the radius versus time. So you can see that the pinch is collapsing at 160 nanosecond, and then there's internal energy for liner on target. So here we are not using gas puff. What we have here, outer liner, which could be high Z gas or solid. In this case, it was maybe argon or neon, I don't remember. But important thing here is that we begin with 12 kilojoule and we have internal energy of 1 kilojoule. So about 8% energy from the driver is coupled to the internal energy of the gas puff load. So those of you students may want to ask, what is the internal energy? It's basically integral of pressure. And if you take Marx bank, here you have a lot more energy, 130 kilojoule, and you can see that the internal energy is about 1.6 1 kilojoule um, uh, from the load. So it's about 0.8%. So you can see that there's a factor of 10 difference in energy coupling when we are talking about LTD and comparing it to Marx-Planck generators. So this is extremely encouraging. This is the schematic of the device. What you see is the brick. This is one brick. One brick consists of 2 capacitors connected to the switch. And in this machine, we have 20 bricks. And I would like to thank Sandia National Laboratories for donating these machines for our experiments here. And then you see power feed taking energy from the capacitors to the load. And this is the vacuum chamber. And this is our load region where we use a variety of loads from wire arrays to gas pops, and we have plans for solid liners. And what you see on the right-hand side is the current waveform average over 30 shots. And if you like to know more about this device, then there's a nice article written by Fabio Conti, which was published last year in Physical Review, Accelerators and Beams. In the chamber, vacuum chamber, we have a variety of ports to field a number of diagnostics. For example, we have laser Schlieren, XUV, framing cameras, soft X-ray diodes, XUV, and XUV spectrometer, hard X-ray spectrometer, bolometers, and so forth. So I'm not going to go into the details. What I'm going to show you some of the results from our experiments. So what you see here is the current, experimental current is shown with a solid line. 0D current is this dotted line. The current we use in Hydra code is shown with this dark blue line. And then you see the collapse trajectory from 0D and 1D model, and the green dots are the experimental parameters. So you see there is a good match with the experimental data with the modeling predictions. So, and we get about X-ray pulses at around 220 nanosecond. The velocity of implosion is about 200 kilometers per second. And the kinetic energy we are talking about is, we know what is the initial mass of our pinch because we have characterized our gas pulse. So it's about 300 joule. And it collapses to 1.5 millimeters. So we have conversion ratio of 9. And when the pinch collapses to the axis, then what happens is inductance increases, and due to that increase in inductance, you see a small dip in the current. These are some of the images we have taken with the XUV framing camera. The time is relative to the bang time or the pinch time. So 0 nanosecond means that this is the time that the pinch has collapsed to the axis, and this is these images are for hollow gas puffs. So we start with the radius of 10 centimeters. It's 1 centimeter, I believe. You can see as the pinch is collapsing to the axis, instabilities are formed, and they are large 1 millimeter wavelength instabilities are formed. And then you can see that after maximum pinching occurring, the pinch breaks into filaments or hotspots. So we observed K-shell X-rays, and full width half max was 2 to 5 nanosecond, and the K alpha yield uh, range from zero point 0.2 to zero point 0.5 joules. And what you see here is some of the diode pulses. We use different filters, particularly to look at the K-shell radiation. We also did experiments with neon. Here, what you see, XUV images with neon. One thing you would notice here is neon is a lot more stable initially compared to argon, or even after pinch, you can see that the diameter is very similar, but the magnitude of instabilities is smaller. So you may ask me a question, why there's a difference between argon and neon pinches. One is more unstable compared to other. There were a couple of papers published in 1990s with reference to dense plasma focus, where we showed that if your Z is below 18, your pinch would be more uniform because they are not radiation cooling or radiation effects. But if you go to Z above 18, then radiative cooling may play a role and give rise to instabilities. I don't have reference to those papers. I will be happy to provide those if you like. One thing I forgot to mention that K-shell for neon is about 0.9 kV, and in this case we saw full width of maximum of 12 to 25 nanosecond, and the K alpha yield range from 2 to 4 joule. I would like to also point out here is that we didn't optimize the pinch to get the maximum K alpha yield. We are planning to do that in future. Idea here was to see how much energy is coupled in LTD pulsars, so that we can compare it to the other experiments we have carried out on traditional Mark span generator. And that's what I show you on this slide. Here, these are argon experiments done on zebra generator, where again you see XUV images, and you see the pinch is very stable, unstable, like we observe in LTD pulsar. Again, I would like to remind, we are not using any mitigation techniques here. As I carried out, mentioned earlier that you can use external Z, external magnetic field, or you can use multiple liner, or you can use liner on target to stabilize pinch. We didn't use that. We are going to do that in coming months. So what you see here is that this 1 megaamp generator, which is 100 nanosecond, I also told you energy in the capacitor bank is about 130 kilojoule. The kinetic energy is 1.1 kilojoule. I showed you on earlier slides. So yield is about 1.3 to 1.9 joules. So you can see that with LTD, takeaway message is with LTD, we can more efficiently couple the energy. So what are our plans? Our plans is currently Fabio, who is in charge of the Z-pinch lab, is doing experiments where he is imploding the liner on deuterium gas. Again, to mitigate instability and see what is the effect on the neutron production. If you're using pure deuterium, then you get unstable pinch, so you have some contribution due to beam target mechanism. So that will help us to understand what is the effect of shell on target in these experiments. And if we use multiple species, for example, if we use double liner argon on neon and then those claps on deuterium, how stable pinch gets and what is the effect on the neutron G. Jeff has carried out those simulations. We are going to validate those simulations with experiment on that.
Farhat, we have one question in the chat.
Sure.
Is there a scaling predicting achievable minimum pinch radius?
So there are factors that determine, I mentioned the pressure, right? You're heating the plasma, so P equal to NKT. So your temperature is rising. There is a physical limit that you can achieve the radius. Basically, you are talking about convergence ratios. So high convergence ratios are very hard to get.
And then there's a comment, this might just relate to that. If the pinch is unstable, then a minimum pinch radius doesn't really make sense.
Yes. What happens is if pinch is unstable, what I haven't spoken here about sausage or kink instability. So what happens when you have sausage instability, like sausage, if you take sausage and compress it with your hand, then you can, what happens is that so think about you have a tube, right? And it's filled with the gas and you compress with your hand. What will happen? Gas will flow in either direction when you are compressing it. That's exactly happens in gas pump Z pinches or any other gas on Z pinches. When you are compressing with the magnetic field and the magnetic field distribution is not uniform, meaning at one particular position, you see the higher compression compared to other, meaning sausage instability. What happens is that the material will flow out of those regions. And as I said, that you have the pressure due to the gas or the material there. If the material is moving out, there is not enough pressure. So what happens is you will start to form the gaps. And that's the next topic. So that's the good question to go to the next topic, which is X pinches, where I will explain what happens when material move out of where you are applying maximum compression. So before I go into X pinches, I would like to show this quarterly and NSA report, which came out actually last week, where Gilbert Collins' PhD work was highlighted. You see here, this is a multi-institution collaboration. So two NNSA center collaborated, our center and Cornell Center. And then we collaborated with San Diego National Lab. Stephanie Hansen was kind enough to do simulations for this experiment. Sophisticated atomic modeling where you have to take not thermal plasma behavior into account, but also contribution due to the electron beam. And I'm going to show you some of those results here. And I forgot to mention Pia. Well, Pia at Johns Hopkins, she also participated in this experiment, and she was supported by an NNSA as well. So this is a unique example where not only two NNSA centers, but also National Lab and NNSA funding PI contributed to this work. Okay. So let me tell you, I know I'm running out of time. Wow, okay, plenty to talk about. What is an X-pinch? X-pinch is, you take two wires and you twist them, and when they form X, this is X pinch. You can have 2 wires or you can have 100 wires. For example, experiments done by Dan Sinnars at Sandia National Lab on Saturn generator, he used many wires. I don't remember exactly how many wires, but more than 20, 30 wires. So what happens is when you're passing the current here, then if you're using 4 wires, then you have twice as much current, meaning you have more pressure here. So you generate a localized X-ray source. This idea came out of a seminar. Someone was giving a seminar on single wires, and that person was describing, or when you have a single wire, you have multiple spots that's happening at different times at different location. If you want to use wire Z pinches for application, you have to have a single spot. And someone in audience said, how about if you make this kind of configuration, then you can have a single spot. And rest is history. And there's been work going on at, in Russia. Cornell has been doing work for 20, 30 years. And at Imperial College, we started work on X pinches, and now we are carrying out at UCSD. However, there are variations. So in X pinches, and I'm going to show why. So X pinches have a variety of applications. For example, this is the radiographic application here. Molybdenum X pinch was used to backlight other molybdenum X pinches, so you can see, you can get the density out, and you can see very fine structure in X pinches. Here, use this for interferometry for getting density information of very dense plasmas. And then Simon Bland at Imperial College use this for diffraction of lithium fluoride in collaboration with the French group. So when we are talking about X pinches, it has 4 phases. When you pass the current, the ablation of the wires take place. And what happens here, what we call here is a local magnetic field, and then you have a global magnetic field. As I said, the current is twice as high compared to the wires. So magnetic pressure is higher here. It pinches the plasma. And what happens is you can see it's a pinch, and then the material starts to outflow and the gap is formed. And when this gap is formed, you generate electron and ion beam. And then when this electron beam interacts with the plasma, it produces hard X-rays. So you have softer X-rays due to the pinching, density going up, and the density going, temperature going up, density going up, and here due to the electron beam. We use, this is the first time that we carried out experiments where we use wire X pinches, laser cut foils, and hybrid X pinches on one machine. I already described what is wire X pinch. Laser cut X pinch is like you take a foil and you take a powerful laser at General Atomics, their trans laser, and you cut the foil in the form of X. And the beauty of this is that you can have whatever shape of you want to have at the cross point to have a single spot. The idea here is that the wire X pinches are irreproducible. There are multiple spots occurring. With laser cut X pinches, you can have a single spot. And hybrid X pinches, you are using 2 conical electrodes, and then you have a very small length wire. Basically, it's a Z pinch. So what you are doing is you are reducing the wire length to have a localized source. Again, I'm not going to go into the details. these are some of the images. So I'd like to draw your attention to these X-ray pulses. You see this softer X-rays, and then you have these harder X-rays. You can see what filters we use. So you have contribution due to X-pinch and then contribution due to electron beam. And we use different diameter wires to get the information about the uh, source size. So with the softer, you see a 5 to 7 micron source size, and with the electron beam, you have 50 to 100 micron source. When we are talking about X-ray cut X pinches, so you can see now you have a single X-ray pulse. You don't have electron beam, significant electron beam effect that we see in the wire X pinch. Now let's go to the hybrid X pinch. With hybrid X pinch, you see single X-ray pulse, some electron beam contribution. So the takeaway message here is the hybrid and laser cut X pinches behave far better than wire X pinches. They are pro and cons for these three types of X pinches, but there's one important thing that we are talking about here. If we want to use X pinches for applications, one important thing is that can we have rep rate sources? And that is the beauty of laser cut X pinches, that you can indeed have rep rate source. Those of you who are old enough know that Walkman tape. So what you do is you take these laser cut X pinches and you put them in Walkman tape, and you rotate and take shots repetitively without opening the vacuum. Again, I'm not going to go into the details, pro and cons. I just pause for a few seconds so you can read it, and it will be on the video as well. And I will be happy to answer any questions later you have. I don't have much time left. The last topic is dense plasma focus. As I said, dense plasma focus has renewed interest due to intense particle source for radiation damage studies or radiation or neutron damage studies. And it is a family of Z pinch. The geometry is different. What you see is the center anode, and then you have outer cathode, and then you have insulator sleeve. So when you apply the voltage, breakdown takes across the insulator sleeve. Due to the J cross P, the current sheet is lifted from the insulator sleeve. It moves due to J cross P force towards the anode tip, and then it collapses in the center, as you see here. So we have carried out experiments on two machines. One is a 1 megaamp generator at test site at Las Vegas, and then we have constructed dense plasma, small scale dense plasma focus here at UCSD. So let me talk about dense plasma focus scaling of the neutrons. So what you see is the peak current and the neutron yield. What you see green is the neutron yield due to thermonuclear fusion, if I remember correctly. And what you see here, the neutron yield, which has contribution due to beam target interaction. What is interesting is if you have a current of more than 1 megaamp, then the contribution due to, in low current machine, the contribution due to beam target neutrons is more significant. And when you go to higher current, then it deviates from it, and then you have significant contribution due to thermonuclear fusion, because the pinch temperature is going up. And this is discussed in Krishnan paper. Again, it's a very good paper if you need to know about dense plasma focus. So since I don't have much time, I'm just going to talk about the experiments we carried out on 2.7 megaamp dense plasma focus um, in Las Vegas. This is the photograph of the machine. This is the current waveform. This is for pure deuterium, and you see the time of flight neutron signal. This is the gamma ray, and this is the neutron signal. Again, the Eric Hahn, he published a paper last year on this experiment in Journal of Applied Physics. What we see is when we add the dopant in the gas, in the pure gas, for example, these are the neutron time of flight data for pure deuterium. But when you start to increase the percentage of krypton, what you see is the multiple peaks disappear and you have a single peak of the neutron. And we carried out experiments at two voltages, 35 kV and 40 kV, meaning the currents were in one case 2.29 megaamp and other case 2.6. But there's a huge difference. When you go to 2.6 megaamp current, you can see there is a significant increase in the neutron yield as you increase the percentage of dopant. And of course, if you increase more, then the neutron yield decreases. So what is happening here is that as you add the dopant, then the radiative cooling takes place. So you will be getting tighter pinches due to radiative cooling. Another interesting thing we found out, if you looked at the graph on the left-hand side, this is I to the 4 scaling, but when we use krypton with deuteron, the scaling changes. Now it deviates from this scaling, so it's much favorable scaling is I to the 6. In those experiments, we did only 2 voltages. Our plan is to complete the scaling with other voltages and confirm that is I to the 6. If it's I to the 6.5 scaling, that's very encouraging for DPF because you want to get more neutrons out with 2 or 3 megaamp current. What you also see, we were not the first one to do the dopant in deuterium gas. There were other folks who studied neutron yield, but at much lower current levels. And you can see that there is no significant difference in the neutron yield at lower currents. But with the higher currents of 2.6 megaamp, you can see a significant difference in the neutron yield when you add the dopant. And we are going to continue this experiment. These are the hydra simulations carried out by Jeff Narkis. He published this paper this year in Physics of Plasmas. Again, I don't have time to go through, but he clearly sees that when you add the dopant in deuterium, then you see the tighter pinches due to radiative cooling, and that gives rise to increased neutron yield. Another thing about dense plasma focus is it's notoriously irreproducible. If you take 100 shots, those won't be reproducible. The question is how you would make dense plasma focus reproducible. And for that purpose, we built this 4 kilojoule dense plasma focus here at UCSD, and you see the schematic of this dense plasma focus. We are studying the structure on affecting the pinch quality, and the unique thing that we are doing is we are simultaneously looking at the breakdown phase, which plays an important role in the pinch phase, and defines what happens in the final phase. Again, I'm going to skip. What I'm going to show that we put some structure on the insulator sleeve, and in this case, we studied X-ray emission, and we see a significant drop in X-ray emission when we use the structure in insulator sleeve. Why that is important? The reason it's important that when you are doing experiments in dense plasma focus, you may have structures on your insulator sleeve, and that could affect the pinch dynamics. And here you see the example that the smooth insulator sleeve, you see this multiple spots here, beam target, you will have gaps formed, so you will have electron and ion beam generated, and then when you have a structure, you don't see this kind of behavior in the pinch, very different pinch behavior. So takeaway message is any structure you have on insulator sleeve can affect the final pinch phase, which can affect X-rays or neutrons. Again, I'm over time here, so I just like to put the summary. This paper was published this year in Journal of Applied Physics. There are a lot more details you can find. So let me stop here, and I'll be happy to answer your questions.
So we have another question in the chat. Farhat, do you want to take there's a couple laid out, so maybe if you, I can read it. Okay, so also, how do you end up initializing the hollow gas puff? Is there a nozzle that sends in the gas? How do you know when things have saturated or reached the appropriate initial conditions? Do you measure the pressure, for instance? E.g., P hits some desired initial value and switches to allow the current to access the load. And there's another one, but I'll stop.
Yeah, so yes, this is a very good question. It is extremely important to characterize the load, because if you don't know initial conditions, you are working in the dark. Particularly if you are doing MHD calculation, you need to put the density profile, initial density profile. Yes, we do characterization. We have a station, what I was trying to find a reference, Fabio Conti has published the whole article on the characterization of gas puffs. And we are planning to do that in STU, which is very hard thing to do, but we have a station here to characterize the gas puffs. And Fabio, if you are online, if you want to add anything to what I just said. This is the paper I was looking for. So Fabio published this paper in IEEE Transaction on Plasma Science, where he in detail describes the characterization of the gas puffs.
And then the second part of that different question, despite the increased efficiency of LTDs compared to Marks-Bank generators, are there methods by which we can quantify how much of that energy goes toward the implosion losses and MRTI? To what extent do we really care to quantify efficiency between machines if energy is lost to MRTI, and may perhaps scale with the increase of that efficiency?
This is another good question. Again, here we use simple models. Of course, you can do, you can learn a lot from MHD calculations, how much energy is going in LTD if you have circuit in your code. But during the implosion, the only information you are getting is from implosion. What is the velocity of your implosion? If there is some way, if you're doing spectroscopy during the implosion and see how the temperature is changing with time, I think that could give quantitative information. But I think that's a hard thing to do. Implosion, you can do Thomson scattering to get the temperature and density out. You can do spectroscopy as well. to get the temperature and density, and that will help to get you information about how much energy is coupled at the clefts. But during the when it's moving in, that is something to hard to do.
If anyone else has questions, feel free to put them in the chat, or if you want to go ahead and unmute yourself and ask, that's okay too. Okay, well, I think we will conclude then. And if anyone wants to stay and ask Farhat a question directly, feel free. Otherwise, thank you so much for attending.
Thank you. I appreciate your time.